It is section 2.3, Newton's method and its variants. The Newton's method is also called the Newton-Raphson method. The objective is to find a 0p of f. So we'll try to solve f of p equals 0. Here the key idea is given. P0 is an initial approximation of p, so initialization, and we'll try to find a correction term h such that this update is better approximation of p than p0. Ideally, the update is the same as the 0. Assuming f double prime is continuous, and we try to use Taylor theorem. So once this 0 is f of p, now the update is good, ideal case, then that is a p0 plus h, and we try to use Taylor theorem. The purpose is to find the correction term. Now, here, assuming that P0 is good approximation, and we can say that P minus P0, that is H, is small, so that this second order term can be ignored. And so this portion is now 0, near around the 0. So we can solve for p minus p0, which is h. That is quite simple. Move this one to the other side and divide by f prime p0. That's exactly this one. So here we define now p0 plus h as p1, because we ignored this portion is not p, and we named it p1. Now p1 may be better approximation of a p than p0. Here the argument can be summarized in this algorithm. The Newton's method for solving f of x equals 0. For p0 chosen close to a root p, we compute pn repeatedly satisfying that equation. Pn minus 1 minus f of pn minus 1 and f prime pn minus 1. That is updated value to become pn. We repeated this iteration to update the approximation. Okay, now the Newton's method can be interpreted graphically. Now P0 is initial approximation and close to P. Then we may get a tangent line at P0, f of P0. Look at this figure. Okay, P0 is given, then we make a tangent line, that one. Okay, this is the tangent line. And we find the x-intercept of y call the tangent line L of x. And so the 0 equal this one, and we solve the equation for x. Then pictorially, that point. Now this x is, if we compare with the earlier one, then that is p1. So here the Newton's method is illustrated in this way. Start with the initial value and make a tangent line and try to find the intercept. That is updated value p1. And now at this point, again, we try to make, again, the tangent line and try to get x-intercept and keep going repeatedly. Okay, that's the Newton's method. For the curve, we need to find x-intercept. The 0 is x-intercept. Rather than curve, we are using locally linear. So it's tangent line, and rather than the curve, the intercept of the curve with the x-axis, and we are trying to get the intercept of tangent line. So Newton's method is using a kind of linearization. Locally linear, the profile is used to get updated. Okay. Here is an example of divergence. The function is arctangent of x. So it's a red curve is the y equal f of x. And if we are using Newton method, start with pi over 2, then it is divergent. Okay, that is pi over 2, and go to the graph and tangent line. This is x-intercept, so it will be P1. Now go to the graph and tangent line, that is P2. And again, go to the graph and tangent line, that is now P3. And if you try to get P4, then it will go far away. And so it is divergent. And the reason is the initial value is too far from the required value 0. So the initialization is very important. Here we have remarks. The Newton method may diverge unless the initialization is accurate. The Newton's method can be interpreted as a fixed point iteration. Once we define the right side as g of Pn minus 1, then that is exactly a fixed point iteration. And now here on the bottom, we have f prime. And once this denominator is 0, then the program broke down. So in theory, we'll assume that f prime is non-zero. And as a matter of fact, the Newton's method is most effective when f prime of x is bounded away from 0 near around the solution P. Okay, now we'll go to convergence analysis for the numerical, the Newton's method. We define first the error in the nth iteration. En is Pn minus P. Okay, then En is Pn minus P. Now Pn is the same as that one, so we are using here, and minus P. Now Pn minus 1 and minus P will make P En minus 1, so that this quantity is the same as En minus 1 minus that one. So by using this denominator, we combine into this one term. Okay, now on the other hand, we are using Taylor theorem to get that equation. 0 is f of p. Now, En minus 1 is same as Pn minus 1 minus P. So that P is same as Pn minus En for any n. That is this one with n minus 1. Now we apply Taylor's, we expand this one and for Taylor theorem, then f of p n minus 1, and that is perturbation minus e n minus 1, and f prime p n minus 1, and here second order term. Okay. The reason we make this Taylor expansion is that this term and that numerator is same except the negation. So that these two addition is 0 means that here this top, the numerator, is the same as that term. Right? Okay, so En becomes now, we have half, and okay, En minus 1 squared, and f double prime at psi n minus 1, and this bottom here. So we reach that equation. And assuming f prime is non-zero, and also assuming f double prime is continuous, and we may consider that this term is a bounded term, so that here this is a shape of En equal some constant c and En minus 1 squared. So anyway, we can write such inequality. So this part is replaced by c. In fact, take a maximum near around here p. This value, maximum of this value here can be used for this c. Okay, here we summarize the convergence of Newton's method. F is continuous up to second derivative, and p is in the interval ab such that f of p equals 0, and we assume f prime p is non-zero. In this derivation of the convergence, we assumed here now that it's non-zero. If it's near 0 or 0, then this value will be very large, so that we should assume this one. Then there is a neighborhood of p such that if Newton's method is started p0 in that neighborhood, it generates a convergent sequence Pn satisfying this inequality. And here also, now another assumption is that P0 must be chosen in a neighborhood of P. That means that neighborhood must be well chosen. So that means eventually P0 must be chosen accurately. If not, then the method may diverge. So along with the required assumption, we prove that here it converges quadratically. That is, when we consider the definition of convergence, and we consider this one as the quadratic convergence, right? So that once error becomes small, then the error goes to 0 very rapidly. Okay, let's see this example. The same arctangent of x. Now start with pi over 5 rather than pi over 2. Then here the output is a sequence. You can see here now it is converging to 0 very rapidly. And I here check the detail, and now along with the 10-digit accuracy is 0, but you can see the detail, print out detail, and I found that here the en is bounded by 2/3 times e sub n minus 1 cubed. This one has third order convergence, so its cubic convergence is obtained. To reason is arctangent is symmetric. For some algorithms, once some symmetry is involved, then it shows some extra convergence. That is called super convergence. For this example, Newton method converges with a super convergence. Okay, here, Newton method for convex function. Assume f is continuous up to second derivative and increasing, convex, and has a 0. Then the 0 is unique. It should be unique because it's increasing. And the Newton-Raphson will converge to it from any starting point. Now, for that theorem, we have here one example. Use the Newton's method to find the square root of a positive number q. Okay, to design an algorithm, we start with here x equal square root of q, and square both sides and move q to the left-hand side. So we have a quadratic equation x squared minus q equals 0. So we define f of x is x squared minus q, then its derivative is 2x. So the Newton method can be formulated in this way. Okay, that is standard form. And Pn minus 1 and f of Pn minus 1 is now Pn minus 1 squared minus q, and its derivative is 2 times x, so that 2 times Pn minus 1. Now, algebraically, we can write in this way. Okay. And here we implement it, and quite simple. For given initial value, okay, we are using p notation, and p plus q over p, and after addition we divide it by 2, so that is updated value. That's it. Now x squared minus q on the right half, it is increasing and convex and has a 0, so that it must be convergent. The algorithm should converge to the required value. Okay, we run the code along with q is 16 and start with 1 and try to make add iteration. Okay, here. So you can see it now. The true answer is 4. So as you can see here now, the error, that portion is error, is a 30-digit and 6-digit, and then now that must be 12 digits, and around the after that, that one will be about 24 digits and 48 digits. Accuracy can be obtained. So it is converging very fast. In reality, if we are using any programming language, and most of the programming language has a command sqrt for square root. If you call the function, then practically inside such computation is done. And the initial value, once you try to get initial value better, then the iteration count can be reduced by 1 or 2. But finding good initialization is also time consuming. And this operation is quite simple. 1, 2, 3 operation. Just 3 flop is finishing one iteration, so that for any initial value, it will work. And also, if you try to put here stopping criterion, then also it takes time. So here, by choosing maximum number of iteration, 8 or 9 or 10, you can get accurate enough the result. So that is practically implemented in the software, in the programming language. Once we start with P0 is -1, and now we try to get the other side so that we can get the quite similar solution, except the difference is only the negation. It should converge to -4. Okay. Now this Newton's method so far is formulated for f of x equals 0. Now, for systems of nonlinear equations, we can formulate the method. And same idea will be used. We are using linearization and try to find the correction term. Now, the correction term becomes a correction vector, and we update repeatedly. Okay, here we illustrate the idea. We begin with a pair of equations involving 2 variables. 2 variables and 2 equations. But it doesn't mean this system has a unique solution. For example, in 2-dimensional area, if this is quadratic and quadratic, then one curve can be given in this way, another curve can be given in this way, so that there are 2 solutions. Now, if the number of equations is the same as number of variables, then here, even though the solution is not unique, the number of solutions will be finite. So in the system of equations, in the engineering applications, the number of equations and number of variables must be the same. If not, the number of equations is smaller than number of variables, then it will have infinitely many solutions. Okay. Okay, 2 variables and 2 equations. Now, x1, x2 is, you may think this one is the current approximation or initial approximation. Now, we try to find the correct correction vector so that this update is better approximation. And ideally, it becomes the solution. Okay, here, so we do the same mathematics. And here, for update, F1, F2, the values are 0. Now we are applying Taylor expansion, and from second order term, we already ignored. Okay. Now, here the main objective is to find the correction vector. So we collect these derivatives, and here, and call it the Jacobian of F1 and F2. We collect them. Then this portion can be written, okay, now F1 and F2, and if we using vector notation, then that collection is Jacobian, and then here H1 and H2, right? So now we know that that is nearer than 0, so that H1, H2 can be obtained by moving this vector to the right side and take inverse of Jacobian. We can get that one, right? Okay. So here, Newton method for the system of equations can be formulated in this way. That new updated vector, the solution approximation is from old one. Now correction vector is added. But the correction vector is a solution of Jacobian times the correction vector equal minus function values. So that is exactly here. After moving to the right side, we have that is a minus function value. So we have to solve this linear system. So that is the Newton method. Here we summarize the Newton method for general system of n nonlinear equations. So that there are m variables. So we should have m nonlinear equations. We can express these m equations as here now vector format. And now in Newton method, we try to find the correction vector, and we make here Taylor expansion and ignoring from second order term, so that this correction vector can be found by solving this linear system. So after finding correction vector, just simply update. So here we have xn is xn plus 1, xn minus 1 plus hm minus 1. Here hm minus 1, the correction vector, is the solution of this linear system. Okay, let's see this example. Starting with 1, 1, 1, we carry 6 iterations of Newton method to find a root of the nonlinear system. Okay, now here, by moving the right side to the left, we can get here terms equal 0. So we'll define, after moving this one here, f1, and now f2 will be this one minus that one, and f3 will be this one minus that. And so that we have 3 nonlinear equations, and for that, and we start with 1, 1, 1, and we'll try to find a solution. Okay, this is an implementation. Look at here. The here main steps are, first here, evaluate the function at the current value. Now that one, x is extra array. Okay, when people are writing this equation, sometimes some people are using xyz, but sometimes people may use x1, x2, x3, or UVW, so that here the user should let the program know which variables are used. So x includes variables in this expression. Okay, so along with that, now, and xyz is, when xyz is current value, f is made, and then by using built-in function, here Jacobian is computed, and H is same as metric inverse of Jacobian times f of x, and along with the negation here, so that xn is updated. So the difference between consecutive iterate must be that update the correction vector. So this portion is printing out and update the value, the x, and the correction vector, which is error. Let's see the result. After, okay, that is now function f1, f2, f3, and the variables are x, y, z, and starting point is 1, 1, 1, and tolerance is 10 to the minus 8, and itmat is 10. Now we call Newton-Raphson system, and after 1 iteration, 2 iteration, 3 iteration, you can see the results here up to 6 iterations. Now, first 3 are the updated approximation for the solution, and the second part is the correction vector, so that that is a kind of error, and as you can see here now is quadratic convergence, and 10 to minus 12 and order minus 6, and here order 3, and so on. So that even for system of equations, Newton method convergence quadratically is really a fantastic algorithm. Once you start with good initialization, it converges quite fast. And here for this problem, the question is, how can we find this good approximation? And I used a graphic tool. So through graph, and if you try to make implicit surface for each equation, then you see 3 surfaces in the figure, and by rotating and moving, and you can point out some point where 3 surfaces are meeting each other. So I chose around there, the point is 1 and 1 and 1. And here, in fact, you can get a better approximation, but I chose the initial point very roughly. Okay? Okay, we'll continue in the second part. Thank you.